You've had a chance to work on a problem here that's up on the board. We wanted to know how far up this car, as a result of being on the end of a spring that's compressed, spring potential energy, right? How far up this hill this car ends up going as a result of that spring potential energy. So what's going on here, really? We got spring potential energy, that's converted to kinetic energy as the spring is released, and that's converted to even more kinetic energy as it goes down this little hill, goes around this loop right here, which car ends up slowing down a little bit as it goes down around the loop, right? Because it's increasing height. As it slows down, we've got kinetic energy being converted to gravitational potential energy now. But then as it comes back down the other side of the loop, the gravitational potential energy is converted back to kinetic. But then as it goes up this straight hill towards the end of the world here, the end of the track, we have kinetic energy being converted to potential. And at some point, when it reaches its max height, all of our kinetic is now going to be gone, and we're going to be dealing with just just potential energy. So all of the kinetic will be converted to potential energy. All right, we have a problem where we're going to say EI equals EF. But we really have to define our points, initial and final. The initial point, of course, is going to be here where the car is on the end of the spring compressed. And the final point is going to be up here where the car has come to a rest. At my initial point, before this car is released, before it's fired off or moving or whatever, what kind of energy do we have? Do we have, let's say, kinetic energy? Do we have kinetic energy at the beginning of this problem? Troy, do we have kinetic energy at the beginning of this problem when it's on the spring? No, we don't. Good. Because it's not moving, right? We have to have a speed in order to have kinetic energy. Do we have gravitational potential energy at the beginning of this problem? Diamond? Do we have gravitational potential at the beginning of the problem? Okay. So the gravitational potential energy is equal to 0. Now, if you define ground level as right here, the gravitational potential is equal to 0. If you define it relative to here, then it's something, right? Now, we don't know what that height is. Doesn't really matter because it makes sense to define it relative to this point, right? So we'll say gravitational potential is 0. As long as we're defining everything relative to this height, or the height that it should have been, had I drawn a straight line there, then it's all good, right? So gravitational potential is equal to 0. If I don't have kinetic energy and I don't have gravitational potential energy, Stefan, what kind of energy do I have? What kind of energy does this car have when it's attached to the end of the spring that's compressed? What's the equation that represents it? Yeah, 1/2 kx squared. So it's spring potential energy or elastic potential energy that it has at the initial point there. All right, at my final point here, when I get up to the maximum height before this car stops, before this car, reverses direction and speeds up in the opposite direction, what kind of energy do I have? Do I have spring potential now, Sonia? Pardon me? When I get to the top here? Is there a spring that's compressed or stretched here? So I don't have spring potential, right? Okay, so 1/2 kx squared is gone now. At the end of the problem, Noah, is it moving when it reaches its max height? So do I have kinetic energy? Good. I don't have kinetic energy. And finally, do I have a height when it reaches the end of the problem? Miles, is it at a height at the end of the problem? It is, so I've got gravitational potential. So I'm going to say 1/2 kx squared is equal to mgh final. Now I can't cancel with the mass because it doesn't appear in every term. Can't cancel with anything, right? Go sub in some numbers here. K is 50, x is 0.15. Be careful with that. M is 0.2 because the mass is going to be kilograms times 9.81 times the final height here. So let's figure that out. On the left-hand side, we've got 0.5 times 50 times 0.15 squared. And then let's divide that by 2 times 9.81. Use some brackets, though. And we're going to get 0.0287, which should round out to 2 digits, is 0.029 meters, or we could say it's 2.9 centimeters. Anybody else get that? What did I do there? Oh, I said 2 times 10 to the power 1. Yeah. So it is 0.29. Okay. Sorry, I just entered it in my calculator wrong. That makes more sense, right? Actually, when you reflect on that, right? 2.9 centimeters doesn't make much sense, right? 29 centimeters makes a lot more sense for a toy car. So 0.29 meters or 29 centimeters would be our answer there. How many people got that? Good. Hey, man, like, you guys see, like, difference between yesterday and today? Even when you guys left here yesterday, some of you are like, oh, that's kind of tricky and so on. But sometimes a night to sleep on it does wonders like that, right? You know what? I think we can have ourselves a little quiz on that tomorrow. Think something like this, something like one of the problems we did yesterday, or something like this. Nice little short quiz, 1-question quiz. Ace it, get a good mark to boost our quiz average up. Okay, that's what we'll do. Tomorrow quiz on this. All right, we're going to move forward here now, though, from that and talk about waves. Yesterday we did a demonstration in class towards the end of class that showed you the 2 types of waves. Waves which, by the way, the sole purpose of which is to carry energy from one place to the other. When we have a water wave, it carries energy from one place to another, from one side of the swimming pool to the other side of the swimming pool, or from the middle of the ocean to the shore of the ocean. An earthquake takes place in the ocean. Sometimes we get a tsunami that's somewhere in Japan or Indonesia or possibly Vancouver or California. Energy is carried from that earthquake by the waves to the shore, whatever. Sound waves carry energy from one place to the other. Earthquake waves carry energy from one place to the other. Every kind of wave carries energy from one place to the other. That's the purpose. Light waves, for that matter, carry energy from the sun to the earth. Although they're not a mechanical wave, they're what's called an electromagnetic wave, but they still carry energy. That's what waves do. They carry energy. And they do it via the simple harmonic motion of individual particles within the wave. So I showed you the demonstration yesterday, the 2 types of waves. There was the transverse wave that looked like this, and there was the longitudinal wave that looked something like this, where we had the series of compressions and then rarefactions, we call them. In both cases, there was simple harmonic motion taking place. In this one, it was simple harmonic motion back and forth this way, and in this wave, it was simple harmonic motion back and forth this way. There's the tie-in, right? We've spent the last week or so talking about simple harmonic motion. Now we're going to talk for the rest of our year about waves, but really, it's the same thing. They just look a little bit different. So our 2 types of mechanical waves, as we addressed yesterday, transverse waves that look like this. That's the typical thing that you think of as a wave. When you picture a wave, you know what? 9 times out of 10, when we picture a wave, we picture water waves, right? Because we've all seen water waves. We can visualize those. That's a transverse wave. But the other kind of wave, which we often can't see, sometimes we can. Showed you the slinky wave yesterday. We could see it clearly yesterday. But oftentimes we can't see a longitudinal wave because it often happens in air. It's where we have the spring or the air molecules or whatever that are squished together and then stretched apart, and then squished together and then stretched, and then squished, and so on. Remember, if something's going to happen in a gas, like sound waves usually are carried through a gas like air, it has to be longitudinal because those particles are bumping into each other, causing the wave to progress, whereas transverse, they've got to be pretty much physically connected to each other to transfer energy from this guy to this guy, and so on. Let's look at a transverse wave a little closer here. You see a graph here of a transverse wave. It's y-axis versus x-axis. So if you're looking at the wave from the side, this is basically what you'd see, vertically and horizontally. Now, there's a few things that I want to label directly on this graph. The first thing is a crest of a wave. The crest of a wave is the bump of a wave or the peak of a wave. When I was your age and learning to drive, or having just learned to drive, I guess, and just got my driver's license, in the province of Nova Scotia, where there's lots of hills, okay, unlike Alberta, we go to the mountains in Alberta, there's lots of hills, but it seems like when we're driving on the highway here, it's just straight flat highway almost. When I was growing up and learning to drive, there was a sign that we had to know that I don't think even exists out here in Alberta. It said blind crest. Okay, have you ever seen a sign on the highway that says blind crest? They're all over the place in Nova Scotia, blind crest. And what it means, what a blind crest means is that you're driving up a hill, you can't see over the hill. So maybe there's a road coming out the other way at the top of the hill or on just the other side. They're warning you that you can't see above the top of the hill, right? You're driving up the hill, you can't see above the crest of the hill. The crest of a wave is the peak of a wave, just like the crest of the hill is the peak of the hill. So this would be one crest. This would be another crest right there. And if we had this wave drawn bigger, then there would be more crests to the right. A trough, well, there's no sign that I ever saw that said blind trough. Okay, but if you think of a feeding trough, okay, like looking at it from the end, okay, a feeding trough, a trough that pigs might eat from, or something like that. The bottom, like a half pipe. Okay, a trough would be the bottom of a wave, because this kind of looks like a half pipe or a feeding trough. Now that's a trough, but that's a trough as well. And if we kept drawing the wave, then that would be a trough as well, and so on and so on. The wavelength of a wave, boy, this is a tough definition. Listen carefully to this one and see if you can make sense of it, okay? The wavelength of a wave is how long a wave is. The length of a wave. Now, that's a pretty simplistic definition, obviously. The wavelength is the length of a wave. What we really should say is the distance over which the wave repeats itself. Okay, when the wave starts repeating itself, we've had one wave. So that distance is going to be the wavelength. Okay? Not quite as simple as saying the wavelength is the length of a wave, but almost. The distance over which the wave repeats itself. Kind of like the period of simple harmonic motion, or the period of circular motion, is the time over which the pendulum motion or whatever repeats itself, right? Wavelength is the distance over which it repeats itself. Now, there's a symbol that we assign to wavelength, because we're going to have to do some calculations with it in a little while here. The symbol for wavelength is going to be, here's a new Greek letter for you. It's like an upside down Y. The Greek letter is called lambda. Why they can't just call it W or something, I don't know, but they don't. Okay, lambda is the wavelength, the distance over which the wave repeats itself. And you can see it labeled in one place up at the top diagram here. This is from this spot to this spot, that's one wavelength. Okay, that's the distance over which the wave repeats itself from crest to crest. Or you could say from this position to this position, because that's the distance over which the wave repeats itself. Or you could say from this spot to this spot, because that's the distance over which the wave repeats itself. Basically, you've got to go through one complete cycle of the wave. That distance between the two is going to be one wavelength, lambda. And the amplitude of the wave, you guys know what amplitude means? Forget about the context of a wave for a second, but just the word amplitude. Where have you heard that before? Amplitude is like the size of something, isn't it? The amplitude of a wave would be the size of the wave, how big the wave is. We're going to label that as a letter A, and it's going to go from the top of a crest to this thing that we call the equilibrium position, the middle of the wave, or we could say it's from the bottom of a trough to the equilibrium position. Just don't make it from the bottom of a trough to the top of a crest. It's not from bottom to top of a wave, it's from the equilibrium to the top, or from the equilibrium to the bottom. We're going to say that the amplitude is the size of the wave measured from the equilibrium position. And we're going to say that it's related to something. Related to, what do you think the amplitude of the wave is related to? If you have a bigger wave, then you have more of this. What's the purpose of a wave? What do waves do? They carry they carry energy from one place to another. If you have a bigger wave, you're carrying more energy from one place to the other. The size of the wave, the amplitude of the wave is related to the energy of the wave. One more little thing before I flip the page here. You see one little note right here about the particle motion. Remember we said wave motion is simple harmonic motion of individual particles? Well, the simple harmonic motion of these particles, if the wave is traveling this way, the simple harmonic motion of these particles is back and forth, back and forth, back and forth, vertically, perpendicular to the way the wave moves. Yeah, that's what happens with a water wave, right? You see this movie or see this video of a ship bobbing up and down in this massive storm out in the middle of the ocean. What's happening to the ship? It's bobbing up and down, right? It's going up and down. Why? Because the particles involved with that wave move perpendicular to the way the wave is moving. If the wave is going this way, then the boat is going to go this way, bobbing up and down, perpendicular to the way the wave travels. All right, take a look at the other kind of wave that we have, which is called a longitudinal wave. This is not a great diagram, so forgive me for that. Best I could do with Microsoft Word, though. It's that wave where we have a series of low pressure areas and then high pressure, and then low pressure and then high pressure. I showed you the slinky wave yesterday where I gave it a push, and you saw where the slinky was squished together. That would be what we would call a compression. The area of a wave, of a longitudinal wave, with high pressure. High pressure or high density. The wave is scrunched together versus the area that follows it and leads it, which is what we call a rarefaction. This one right here, which is the area of a longitudinal wave with low pressure or low density. If the wave is traveling this way, and the particles are vibrating back and forth this way, it's simple harmonic motion again, but it's simple harmonic motion parallel to the way the wave is moving. All right, we're going to finish off the day with a little bit of wave speed, a little bit of quantitative analysis about the wave. Now remember that the wave speed is defined as how fast the wave is actually traveling, but we're not talking about the particles of the wave, Gianna, just like you were just asking me about. We're not talking about the particles moving at that speed. We're talking about the wave itself moving at that speed. The particles are either bobbing up and down in a transverse wave, or they're going parallel to the wave in a longitudinal wave, but they're not going all the way with the wave. They're not traveling at that speed. Because any wave, unless it reaches a new medium, a new material, is going to travel at a constant speed, we're going to describe the motion of that wave by our group A equation, V equals delta D over delta T. When a wave goes from one material to another, the speed can change. When light goes from air to glass, the speed changes. And it changes, because it changes speed, it changes direction. And because it changes direction, it allows us to see the glass. It's called the refraction. When water waves go from deep water to shallow water, the speed changes as well. But as long as the medium stays the same, as long as what it's traveling in stays the same, then the speed of the wave doesn't change speed. It stays the same. Medium stays the same, speed stays the same. V equals delta D over delta T. Now, we're going to tailor this equation to wave motion. This is a general equation that's valid anytime something, including a wave, is traveling at a constant speed. So we can use this here. But we can also tailor this to make it unique to wave motion. Tell me what the distance over which the wave repeats itself is called again? Yep, the wavelength. So we're going to say the distance, specifically the distance over which the wave repeats itself, the distance for one wave is the wavelength. What's the time over which the wave repeats itself? If we're going to replace d with lambda for distance over which it repeats itself, then what's the time over which it repeats itself? Jenna? Good, it's the period. So we're going to say v is equal to lambda over t. Now that's a good equation. Now the way you usually see it written though is a little bit different than this. Usually we end up substituting t is equal to 1 over f in there. It becomes v is equal to lambda over 1 over f, which becomes v is equal to f times lambda. If you look on your data sheet under simple harmonic motion of waves, you'll see that equation v is equal to f times lambda. It really is just this equation tailored to waves, but because it's so commonly used, we're going to write it down as a separate equation. Let's do a problem on page 409 here. It says, to generate waves in a stretched spring, you oscillate your hand, simple harmonic motion of your hand, back and forth, at a frequency of 2 hertz. If the speed of the waves is 5.4 meters per second, what's the wavelength? Look, this is a frequency. This is our speed. We want to find the wavelength. We're allowed to use v equals d over t here, but it's probably not very prudent to try that one. Okay, we might as well try the one we just learned. V is equal to f times lambda. Rearrange it to solve for lambda. F goes down, becomes v over f. Becomes 5.40 meters per second divided by 2.00 hertz, which gives me 2.70 meters. The length of the wave, how big this wave is, how long this wave is, 2.70 meters. The distance over which the wave repeats itself. All right, we'll finish this off with a few practice problems on what we just learned. Remember, v equals d over t, v is equal to f times lambda. Anytime the wave is traveling in a medium and as the medium isn't changing.